Hello, and welcome to Palisade Corporation's webcast, At Risk for Engineers, presented by Andre Kleyner of Delphi Corporation. My name is Jamison Romeo Hall, and I will be your host today, and I'll be available to help answer WebEx technical questions by chat. If you experience technical difficulties joining this WebEx session, please dial 1-866-229-3239. At this time, all attendees are in a listen-only mode. Please note that as an attendee, you are part of a larger audience today. The attendee list is suppressed to maintain attendee privacy. We will be holding a Q&A session at the conclusion of today's presentation. You may ask an online question anytime about the presentation today by clicking on the chat icon located in the floating toolbar. I would also encourage you to visit our website and sign up for a free trial download of our software, including our lead products, At Risk, and the Decision Tools Suite. We invite you to sit back and relax and enjoy today's presentation. Andre, you have the presenter ball.
Okay. Can you hear me well?
Yes, you sound great.
Okay, excellent. Because I'm on the speakerphone, I can take a receiver if I need to.
Okay, great.
Okay.
Your audio sounds good.
Excellent. Okay, let me. I'm not sharing it yet, right?
Right.
Okay, share my desktop. Okay, now
Looks good.
Okay, now it's sharing.
Yes, perfect.
Okay. Hello, everybody. It's a pleasure to actually speak today. I was going to say good morning, but I understand that we have listeners from other countries, so it's a good morning, good afternoon, maybe even good night for some of you. Okay. I put a little bit of my bio, which you can find on my website. I'm not going to read it in detail. I just want to mention a couple of things. I do come from the industry, so I spent over 25 years working in the industry in engineering and research and a little bit of a managerial stuff. But I also have exposure to academia. I'm part-time teaching adjunct professor at Purdue University, and I'm going to talk a little bit about my experience as trying to teach students and beginners Monte Carlo. This is actually going to be part of our discussion today. So what I'm trying to do in my everyday practice is kind of trying to get best of both worlds, so trying to be as practical as possible as an industry guy, but at the same time trying to bring a little bit more rigor to things I do. So with that, let me move to the next slide. And like I said, I have a website, andre-kleyner.com, so you can find my bio and a little bit more information there. So here's the outline for today's webcast. So since the title of this webcast is At Risk for Engineers, obviously we're going to talk about engineering problems, and specifically about engineering problems which actually benefit from using Monte Carlo simulation. But with that also, I'm going to talk a little bit about teaching Monte Carlo, and this is more like how you transition from observer to actually practitioner and start using Monte Carlo, because I'm a big fan of Monte Carlo methods, and I noticed that there's still a little bit of level of engineers being a little bit uncomfortable seeing Monte Carlo is something requiring a lot of computing power and a lot of statistical background and basically a lot of expertise. But my goal is basically to explain people that it's actually much simpler than it sounds, and I'm going to show you a little bit of a practices I use in teaching Monte Carlo, kind of make it simple and then increase complexity a little bit. I'm going to talk a little bit about the book I actually co-authored It's called Practical Reliability Engineering, which actually has a chapter on Monte Carlo and also some at-risk applications. Don't worry, we're not going to turn it into a book promotion, but some of the practices I use actually I try to write down in that chapter. So some of that we're going to talk today is in the chapter, and also there's other applications of using Monte Carlo simulation in reliability practices in this book. Part of the training when we get people to become users of Monte Carlo simulation is actually starting them on something they're more familiar with, like Excel, and transition to at-risk, because at-risk is Excel-based. Then I'm going to talk a little bit about, I have several examples of using Monte Carlo in different engineering practices, and specifically about using best fit function to analyze engineering data. And that really kind of comes very handy when you do Monte Carlo simulation or processing the data when you're trying to understand what are the underlying statistical distributions. So this is our outline for today, and I understand there's a different levels of expertise of using Monte Carlo simulation of people calling in. So what I'm trying to do, I'm kind of trying to hit several different level of expertise with both Monte Carlo and at risk. So I'm kind of trying to target several different groups of audience with this. Okay, so moving on to engineering applications of Monte Carlo. And this is non-exhaustive list. And going back to my biography, most of my industrial expertise is in something I call dark side of engineering. It's kind of, we use it as a joke, but basically dealing with things, how products fail. So that's where dark side. So reliability, quality, designing to specifications, which actually if you don't design to specification, then it constitutes failure. So here's some applications, and in no way this is an exhaustive list, because there's many more applications. This is what I'm listing here is basically what I have some experience with, and had a lot of opportunities to apply Monte Carlo. So technically, any problem, any engineering problem or non-engineering problem where you need to model uncertainty. So that's nothing new here. So some of the examples include exceeding the maximum allowable threshold. That goes for, actually we're going to look at one example, like if it's maximum allowable stress level, or if you're electrical engineer, you're designing a circuit, and your circuit should not exceed certain current or voltage. So anything dealing with certain maximum allowable threshold. Electric circuit analysis, I'm not going to talk about this today, but actually some of the electrical circuit analysis tools like Mentor Graphics, they actually have built-in Monte Carlo tools, but sometimes the problem is people, the electrical designers who use those tools, they don't have enough understanding of Monte Carlo simulation. So when they see the results, they don't always know how to interpret them. So still, like if you have that tool built in, it always helps. Basically, you have some basic understanding what you're actually simulating with that. My favorite subject is reliability, of course, and we're going to talk a little about load strength approach. I mean, how you can predict reliability, and I have an example. Quality also is a very good example for applications for Monte Carlo, like process capability. If we have time, I'll get into this a little bit. Tolerance stack up. Yeah, if you mechanical engineer, designer, yeah, you know everything has tolerance. And sometimes when you have multiple parts, you need to understand what kind of resulting tolerance you're going to be dealing with. And it's not like you just add them up. Or it's a little more complicated than that. precision design and also design for Six Sigma. Yeah, that's another perfect application for Monte Carlo simulation. You're dealing with a lot of variables and with variations. You're trying to understand what your output is. Warranty forecasting. So when you're trying to forecast what's going to be your returns and the cost, how much you're going to pay for that, and I also have an example, again, in kind of simplified form for that today. And my last bullet is et cetera, et cetera, et cetera. It's like I said, I'm sure people on the phone can come up with their own examples where to apply Monte Carlo simulation. Here's kind of generic slide where it's showing that Monte Carlo simulation can be applied to various aspects of design. So this is kind of generic diagram showing that, yes, you design something, and if you need to design this robustly enough, you have to understand, and you have multiple variables, and those variables, a lot of them random, like environments. Yeah, if you design like something I'm involved with, designing automotive parts, let's say your radio, and you need to understand that you're driving your car and there's a lot of vibration and also temperature cycling and a lot of other environmental factors. Also customer usage, people, pushing buttons differently and some kind of push them too hard. So that also variable. Materials, yeah, we assume that we know the material properties, but actually they also may be random, and there's also tolerances on dimensions and material properties. And like I said, there's multiple variables and all those inputs, and more complex your product is, then basically the more the effect of the uncertainty and effect of randomness of those input variables. And with that, you need to understand, like if you have certain parameters of your product, the performance, for example, yeah, if you have that radio, you don't want too much noise with that radio, and you want to perform to specification, and also you don't want it to fail. So that is also a factor. Like I said, this is pretty generic approach to engineering, but that kind of shows you the essence where Monte Carlo simulation can be very useful. So you're assessing performance, quality, reliability, and a lot of other factors. And if you understand your product well enough, and if you can model those input variables, you can have a pretty good understanding of what's going to come out as a result of your design. Let me talk a little bit about this book. Like I said, this is a book called Practical Reliability Engineering. So if you're involved in design and in understanding reliability or assessing reliability, obviously I would highly recommend this book in my highly biased opinion. But actually, and I'm going to come back to this, but what you see here is probably see the highlights in red, chapter 2, 4, 5, 7. But basically, those chapters deal directly with statistics and Monte Carlo simulation. And chapter 4 is basically dedicated to teaching Monte Carlo. Interesting thing is, when we were working on 5th edition of this book, and I definitely wanted to include Monte Carlo, I did some search, and what was surprising, there's a lot of books mentioning Monte Carlo, books dedicated to Monte Carlo, but it seems like it's always kind of extreme. Either you get the book just about Monte Carlo with all details and modeling and all the hardcore mathematics going into this, or you got the book kind of on the other spectrum where someone mentions Monte Carlo in maybe several paragraphs, or maybe sub-chapter like 4.2.1, where it says, yeah, this Monte Carlo is a great method, and you can model things and you can simulate inputs and get the outputs. but it's like none of those were, in my opinion, were good for engineers, because you don't want to spend like a year studying all those mathematics where you need to become a practitioner, and the other books, the engineering books, were basically not giving you enough information to understand. So what I was looking for is like a one good chapter where like someone with engineering background could read that chapter and basically have enough understanding and become a user. And lately, teaching to students, I actually was using the material we put in that chapter. So I'd like to think that we achieved that goal, but again, it's my highly unbiased or biased opinion. Okay, try to move to the next slide. Okay, so in trying to educate, and I'm talking both about students, and also I do some internal training since Delphi, and by the way, Delphi is one of the major automotive suppliers. So we supply basically to every car manufacturer there is. So whatever car you drive, Toyota, Honda, GM, or even Tata Automotive, you have Delphi parts in it. So it's a global company, so I've done a lot of internal training and trying to get people start applying Monte Carlo and then practice it. So the approach was the same. In that course I was teaching at Purdue University, it's a systems engineering course. That's not a statistics or not a Monte Carlo simulation course. So I just needed to kind of get people start using it quickly and get them understand the method. So if you explain the simplicity of the method, then you explain, and again, the idea is people usually comfortable with something which they already know, and most, if not all, engineers know how to use Excel. So that's a good start. So you start with Excel, and basically we do Monte Carlo as a first step. We do Monte Carlo with just using Excel, and I'm going to show you. I'm going to switch to Excel spreadsheet from here with no at-risk, nothing else, no macros, just plain good Excel spreadsheet. Then I assign a problem in Monte Carlo simulation with Excel and try to just make students comfortable with using it. So, and then when they have a pretty good understanding and see it's not that difficult, then you kind of move forward and show them that you can do it a little bit more with a little more sophistication, and then you can show them specialized software like at risk and basically how much extra you can get from using it, some extra information, and you can do correlated inputs or uncorrelated, and have a pretty good analysis of your data, like tornado graphs. But the bottom line is the goal here is not to teach engineers or engineering students or engineers in the company how to do their job, but rather like how to apply Monte Carlo simulation to their projects they're working on or to basically their jobs. Okay, so this is a pretty simple example we usually start with, and since most people study physics, they know that the stress, mechanical stress, is calculated as force applied to an area. So basically, force divided by the area. In this case, we have area with dimensions A and B. Something really simple. Like I said, this is the first step to get people into Monte Carlo simulation. So pretty simple, stress equals F divided by A times B. But the question is, okay, basically all those variables are random, and even though we think we know A and B, but in real world they have tolerances. So, and also force, in this case, in particular case I assign them, is random force. So again, stress is random variable, and you need to be evaluated and compared to a target. So I set up a target and say, okay, in my design, my force should not exceed certain value, and that's going to be my next slide. Not this slide. I kind of like this list cartoon. So how do you want it, crystal mumbo jumbo or statistical probability? What I actually tell the students is Monte Carlo is actually the second best way to forecast things. I mean, the first, obviously, crystal ball. If you have one, that's great. That's the best thing. But if you don't have one, then probably Monte Carlo would be a good second option. Okay. So the next step basically here is like I give them really a brief explanation. Okay, what Monte Carlo does. It's basically a brute force method, and we'll go back to that simple example where you have what's called transfer function. In this case with stress, it's basically how you calculate stress. It's force divided by A times B, and then you have random inputs coming into which you process with this transfer function, and you get the output. And the output, when you simulate those random inputs, your output obviously is also random, and that's what you get at the end and do the analysis of your output. And the key here is that basically when you have random inputs, there's really no way to solve this analytically, and the only case I'm aware of where you can solve this analytically when you have actually sum of normally distributed random variables, then your output is also normally distributed random variables with variable with the mean, which is equal to the means, sum of the means in standard deviation is square root of sum of squares. But that's the only thing I can think of. Everything else is basically Monte Carlo is pretty much, if not the only way, but the best way to solve this. Then I kind of do a little bit of joking and say, okay, what do you need to run Monte Carlo? You need the latest XK6 Cray supercomputer. You need to have PhD in statistics and specialize in very expensive Monte Carlo simulation software. But then say, okay, no, actually, you don't really need any of that, and you can do Monte Carlo pretty simply. So you just need a regular PC, and Mac actually will do the job just fine. You can't use your cell phone for that, at least not yet, but I haven't tried. You need to have a basic understanding of statistical distribution, both discrete and continuous. And you can start just with simple Excel spreadsheets without even knowing how to use macros, just basic Excel. So for that, we move into the section where we basically try to do Monte Carlo with just plain Excel. And most of the people know that there's a random generator built in Excel, which is called RAND, which generates the random numbers between 0 and 1. Most people know that. But actually, most people don't know that you can use that function to model pretty much any statistical distribution. You just need to actually use it a little bit differently. So when we start with kind of rectangular distribution, you can change that 0 to 1 to basically A to B by just using this function, A plus B minus A times rand, that function. And there's even a built-in rand between function, which if you need to generate only integers, like if you're trying to model, I don't know, sales volume or attendance or something. Then there's also a very useful distribution, which is, it's not classical distribution, but actually it's very commonly used by engineers, which is triangular, where you know the maximum, most likely value of a variable, and you know you cannot go below this value, in this case A, and you cannot go above another value, B. And it's often used to model tolerance this way. So you have a triangular. And also, it's this is the equation for symmetrical. It's also very easy to model in Excel using just that rand function. Then actually moving something a little bit more complicated, like normal or log normal distribution. And again, I mean, most people on the call probably very well with normal and log normal. And again, it's a pretty simple function, Excel function, where you can model both, like norm inv or log inv function using that random generator. Again, it's there. It's just most Excel users don't know that. If you want to get more fancy, like going to Weibull distribution, and if we have any reliability practitioners, it's probably one of the favorite for reliability people. Also, it's no big deal. You can also model Weibull, both 2-parameter and 3-parameter Weibull, just with Excel, with that equation at the bottom. Another popular distribution among reliability engineers is exponential, which is actually a special case of Weibull, and obviously it's even easier to model. But also in the book, I put together a table for many other distributions, how you can model them in Excel. So for the convenience. So going back to that simple example, so we have random force applied to area A times B, and we assign certain parameters. Okay, so the A is 2 centimeters with a tolerance of ±1 millimeter. B is 3 centimeters with tolerance 1.5. And with force, I make it a little bit more complicated. Let's say we don't know what this force is, but we can take some measurements and basically try to come up with appropriate distribution. And the goal is, so the structure is expected to function properly within elastic strain range, where the probability of exceeding the yield strength of 30 megapascals, which is 30 times 10 to the 6 newtons per meter square, needs to be estimated. So the idea is, okay, see what's the probability of actually exceeding that number with the data we're given. Okay, so with that, let me go to my Excel spreadsheet, something I start with. Okay, this one. So again, the idea is to make a first step before moving to at risk, to do a simple Monte Carlo simulation with what we have. So I kind of cheated here a little bit, and I put most of the information in already, because what I noticed is when you start actually doing a demonstration, things just don't work for some reason, especially over the internet. So I already programmed the equation. So here's my A, which is I defined as triangular distribution right here. And here's how I modeled it. Again, just a simple Excel equation. You can see it at the top. So it's 2 centimeters ±1 millimeter. Very similar for B right here. So here's the value, 3 centimeters ±1.5 millimeters. Now the question about function. Before we start using Excel, I actually assigned, I say, okay, this is this distribution, so just use this. But since most of the people here on this call are at-risk users, so I'm going to use the distribution fitting. So right here, I hope you can see that I highlighted. Basically, I collected 200 data points. I just took those measurements of that random force, and now I'm going to try to find the best fit distribution for it. Okay, I'm going to go down, hit the best fitting distribution to the data. Okay. Okay. I know there's about 2 seconds delay in what I'm showing, so I'm going to stop for a second. So And as probably most of you know, you can use 3 different criteria for finding the best fit distribution. So chi-squared, Anderson-Darling, and Kolmogorov-Smirnov. So for Anderson-Darling, it gives me Weibull as number 1. I'm going to switch to Kolmogorov-Smirnov. It's also Weibull is number 1, but when I switch to chi-square, actually it's also Weibull number 1 because I thought it was number 3. Anyway, so Weibull seems like a logical choice. So here's the parameters. The beta, or the slope, is 2.52 something, 9N21. Again, before with students, I only have 1 lecture, so I don't have much time going into best fit distribution. But again, here I collected the data. So what I'm going to do, I'm just going to program the distribution I just found using best fit into this cell D5 as a Weibull distribution right here. So basically, we are pretty much done. So what I'm doing here is we got A, we got B, we got F. And to calculate the stress, all I need to do is basically F divide my F by A times B. But since we need to do many runs, and there's different ways of doing it in Excel, but the simplest way is just to copy this whole thing down, and I'm choosing arbitrarily 2,000 runs. So I'm basically copying it down for 2,000 rows down. And as you can see, in each row, I get my own set of A, B, F, and the resulting stress. So, okay, let me remove this. Like I said, I tried to do something beforehand. So what I get at the end is the column E, which is the column of 2,000 values of my stress. So, and I can do a lot of things with that. So I looked at the mean value, I looked at standard deviation, minimum value, maximum value. But what I'm really interested in is what's the percent of those values exceeding my maximum allowable value, which is 30 megapascals. So what I'm having here in the yellow, another yellow cell G10, is basically the counts, the percent of number of rows where actually that number exceeds 30 megapascals. So in this case, it's 1%. But if I keep hitting F9, which does recalculate, that number changes. And again, I understand there's a delay a little bit, so you probably see that number was 0.8, now it's 1.65, 1.15, and so on. So it keeps changing. But obviously, I only use 2,000 rows, so my model is not probably not converging too well. So if I use, instead of 2,000 rows, I use 20,000 rows, that number will probably be much more stable. But again, the idea here is not to solve any particular problem, but rather explain the method, how it works, and it basically it's a real simple, straightforward approach. And once you get those outputs, you can do a histogram, and if you need to get a little more fancy, say, okay, what kind of distribution is that? And also, I can go back and again, if I know how to use at risk, I can actually see what kind of a distribution I'm getting at the end. So I'm going to do a fit distribution to a data. Okay, so it tells me, yeah, I got seemed like beta general or gamma. Let me go to Anderson-Darling. Yeah, actually it seemed like my resulting distribution for the stress is also shaped as Weibull. And this thing will tell me if I move this thing. Okay, so it tells me, yeah, I'm about 1.5%. My tail above 30 megapascals, about 1.5%. But again, with students, when I teach it to students, we're not there yet. because we're still within realms of Excel, and that's where, like, okay, you get all the statistics, percent, and you can do a histogram and just see how your data looks like. And again, going back to my presentation, again, just for simplicity, all we did is programmed this equation in the middle. Let me get a little more fancy. I'm going to annotate this. So this is the equation, which end up being programmed in that cell, where all you're doing is basically calculating the stress as a ratio of 3 random variables and do 2,000 rows. And like I said, that was an arbitrary number. Okay, let me go back. Okay, so moving on to something a little more complicated, which is quite popular in reliability, is what's called load strength calculations, and sometimes referred to stress strength calculations. I know there was a webcast, Palisade webcast in October by Dr. Naresh Samtani, who actually talked about this a little bit, but as it applied to civil engineering, and I believe civil engineers use term load resistance. But again, I'm going to be staying within realm of reliability engineering, so we use mostly stress strength or load stress. But the idea is I wouldn't call it very simple, but simple enough. So you have strength when you design your product, and if there's certain ways you can measure strength, and that doesn't have to be physical strength. It may be variation of your output parameters or performance. And you also have load or stress you apply to your product. And the idea is very simple, that where actually load or your stress exceeds the strength of your product, and again, it doesn't necessarily apply to mechanical properties, then actually that's where you have failures, where stress kind of kills your product because your strength is not good enough. So it's a wonderful concept, but one of the problems with using it is basically where to get the data. As far as the strength, that's a little bit easier because you can measure the variation of your product. But as far as stress, that's a little more difficult because you don't always know what kind of stress your environment offers. And the stress, again, it may be a vector of many parameters where your stress is different environmental conditions, different user applications. Like going back to my example with car radio. I mean, first of all, different people listen to radio differently. I mean, some people hardly ever turn it on. Some people just turn it on and it's on all the time. And especially if you're a pizza delivery guy with radio on, you're going to crank up quite a few hours. And also, maybe somebody's driving over potholes a lot, but someone driving over just smooth roads. Again, there's a lot of variances, and that often creates that often creates a problem to actually gather the data and understand those the parameters of those distributions. We're going to do one example where I'm just, again, I kind of simplified it for the presentation purpose, but just to give you an idea where you can gather data and maybe in your practice, you can do something similar and maybe do analysis of your, estimate your reliability up front or see how well your product is performing. So here's an example with the washer. So washing machine manufacturer is estimating the motor warranty due to fatigue failures for the first year of operation. And on average, that amounts to 100 cycles for the motor, 100 full cycles. I mean, don't read too much into the actual values. I mean, some of them made specifically for the example, but I mean, if, again, in your practice, you can do similar measurements and come up with your own numbers. So, so the actual washing load sizes for the motor vary depending on the way that user run each machine. Yeah, obviously someone puts a lot of clothing in it. Some people maybe not. So here's the data with maximum loads. That's the table. So and the data indicates that 4% of the people use a maximum load of 2 kilograms. Then 42% get up to 3 kilograms. 40% up to 4 kilograms, and that's what you see in the middle column. So now we're trying to take this data and basically convert it into cumulative distribution function, and that's what you see in the third column. So basically, it's nothing but adding those percentages in the second column together. So 4, then 4 plus 42, then it's plus 40, 86, and kind of showing that 99.7% actually don't go over the maximum allowable load of 6 kilograms. So that kind of gives us an idea of what kind of load or what kind of stress we're dealing with. Now let's move on to defining the strength, which can be pretty tricky in real life. But again, in this example, I'm trying to simplify things a little bit, and you can probably use the same concept. So in this case, the manufacturer conducted a series of tests to failure at different machine loads. And even though it says the maximum allowable load is 6 kilograms, we know people don't follow that. So we did basically 5 series of testing at different loads, like 4, 5, 6, 7, and 9. That's what you see in your left column. And doing test to failure, what we learned that at the maximum load of 4 kilograms is a 2.73. That's the second column in that table. Percent failed at 100 cycles. It's not necessarily we saw that at 100 cycles. There's different ways of running test to failure. Maybe we exceeded that number. Those are details. It can be done different ways, but here's what we learned. And when we run at the maximum load of 5 kilograms, then 10%, but a little over 10%, again, the second number here, failed at 100 cycles. At 6 to 20.6%, and so on. So now we have some idea about the strength of our product. So now we need to put this together. So let me go back to my Excel spreadsheet, and again, I did a little bit up front without, because I wasn't sure if everything's going to work as designed. So now what you see here at the top, I'm highlighting it. Those are just 2 tables I just showed you in the presentation. So now what we need to do, turn those tables into actual distributions. So in this case, I'm again going to use distribution fit, but in this case, it's not just simple data. We're dealing with something similar to cumulative distribution function. So what I'm going to do is I'm going to try to fit this data to a distribution to this data. So I'm going to pick, but now instead of just continuous simple data, I'm going to use cumulative. And for cumulative, I need basically 2 columns of data, and that's what I have: maximum load and percent users. We're still talking about the load. So I'm going to fit. Okay, so that's how it looks like. Gives me inverse Gauss, log normal. Again, if I go, actually in this case it only gives me, since I'm analyzing cumulative data, it's a CDF type data, so it doesn't give me too many options. Basically curve fit. Okay. So seemed like my best choice in inverted Gauss, and so that's what I put in this cell, which says load. Now I'm taking this data. Now I'm trying to estimate my strength. So I'm doing pretty much exactly the same thing. Cumulative. Okay, that gives me beta general. Okay, sounds good. So, and then I basically plot, not plot, I program those as risk outputs, as load strength. But again, what I'm interested in is basically cases where strength exceeds my load actually exceeds my strength. So also I create another cell where it's a difference between strength and the load. So now I'm ready to run Monte Carlo simulation here for each one of them, but mostly I'm interested in this difference between strength and load. Okay. So let me, yeah, like I said, I ran most of those in advance, run simulation. Okay, you could probably see the window changing. Okay, what I'm going to do now, I'm going to stop this since I just to save time, since I already created those charts. I mean, most of you know how to use Monte Carlo, so you know what's going on here. So I'm going to stop this simulation, okay, and show you the results. So first of all, here's a graph I created, and that's my simulation of strength minus load. And that's where we see it's actually, it should be greater than 0, but there are cases 1.4% when actually it's less. So that's what I'm worried about. So this kind of gives me the idea of what is going to be my unreliability, which is, like I said, in this case, 1.4%. Also, if I want to get fancy with at risk, then I can overlay two graphs together, load and strength, and kind of show where they overlap. And again, where they overlap, that's where I don't want to be. Okay, we still have a few minutes, so I'm going to move on to the last example. Again, I have many more, but with the time we have. So the next example, and where I've probably used Monte Carlo most, at least a few years ago, is warranty forecasting. And I made again, for presentation purpose, I made a really simple example. In reality, those models are much more complicated. But again, the complexity is not in modeling. I mean, it's just more variables. And again, for the presentation purposes, it just would make things more complicated. So here's my warranty cost. Again, it's a simplified, very simplified model. But in automotive, most of the standard warranties are still 3 years, at least on most parts. And the way to calculate sale is take a sales volume, basically the total population of parts in the field. And then I need to multiply it by my unreliability, meaning the percent, because since reliability is a percent which survive, but I'm interested in percent which will not survive. So I'm interested in, I multiply this by unreliability. So my percent which will fail, so 1 minus my reliability at the same time mark at 3 years. Then here's an interesting thing we also need to be aware of. It's called NTF, no trouble found. It's at least in the electronics industry, it's a big factor where actually parts come back from the field, you do analysis, and really nothing wrong with those parts. And different manufacturers handle that differently. But I mean, if nothing wrong, and especially if you're a supplier, in many cases you're not responsible for warranty. If it's still working, maybe it was some misuse or somebody didn't know how to read the manual. Again, it varies from case to case, but in this case, I'm going to simplify it and say, okay, but no trouble found, we're not responsible. So basically what I'm interested in is a complement of no trouble found, because no trouble found is % of what I'm not responsible, but I'm still trying to calculate what I am responsible for as a manufacturer. So I'm using 1 minus NTF %. And that I multiply by warranty cost per repair. So, and that obviously varies quite a bit. So we have several random variables here. So again, sales volume times unreliability, % fail, times 1 minus no trouble found, something I will be responsible for, times warranty cost per repair. Okay, so let me go back to my Excel spreadsheet. Okay, I'm trying to kind of make it more visible using colors. But again, here's that main equation with warranty cost, 3 years. And modeling warranty cost per repair, again, this is based, I have access to my database with cost of repair, so I'm analyzing that and coming up that the best distribution fitting it is log normal. No trouble found. I can actually show you the data where this particular case came from. So again, as applied to automotive warranties, let's say we're looking at vehicle components, and I'm not naming them for obvious reasons, but let's call them vehicle component 1, 2, 3, 4. So I have a % of no trouble found and total parts which came back. So something like in this case, in row 2, I had the chance to analyze 843 parts, and turned out that 125 of them, there was nothing wrong with them. So here's my %. So here, basically, what I do, I collected, in this case, 42 different components, and go and do the same thing with distribution fit. So in this case, it's just continuous sample data and do the fit. Okay, and funny if Weibull also comes up. I swear I didn't I didn't set it up like that. But also, what is important to remember in this particular case, %, we talk about %, it cannot fall below 0, and it cannot go above 100 or 1 in this case. So it's also important if I am, and Weibull does have tails, and also in this case actually has a shift. So it's also important in this case to model it correctly. So not only using this particular distribution, I also need to truncate it, make sure, okay, this number will never drop below 0 or go above 100% because it's just not realistic. So this is also something to remember. Okay, so here's my data. Now I'm going back to my modeling spreadsheet. Okay, and let me see. Okay, so basically all I'm doing is programming this equation, warranty cost. Here's my NTF. Oh, another thing what I'm doing here, just kind of make it interesting, I'm using reliability equation as exponential distribution, and since in this case it's actually written in deterministic form because you know time, you know lambda. So in this case, actually, I made my lambda, which is failure rate, the parameter of that reliability distribution, as a random variable. I just model it as a triangular distribution with a failure rate between 0.01 and 0.02 failures per year. Again, I made it for simplicity, it's per year because my warranty is calculated in years. Okay, so with that, risk output. Again, I'm going to start simulation here. Okay, this is my warranty cost. Yeah, I'm going to stop this simulation. So it's just showing the warranty cost, and I already ran this. So it just was going to show the method. And where's my graph? Oh, there you go. Actually, it came out pretty is a pretty nice histogram. gram right here. So my value is in millions. And obviously, once you get this result, you can do a lot of things with it. You can estimate what's your maximal, what's your mean in 50% confidence, but also if you want to kind of be a little more conservative, you also can look at the higher confidence levels. And again, this is kind of important because the warranty cost is something which is built into product. So like you start selling product today, but according to the law, you already need to accrue certain amount of money for future warranties, and that's a law in many countries. And those warranty forecasting actually quite important. Okay, so with that, I'm almost finished here. Okay. I was going to talk a little bit about other considerations like convergence and model sensitivity, which can be very high to certain inputs. A correlated input, sometimes what we forget about, and something can mess up your model because you assume they're not correlated, but actually a lot of inputs are correlated together, and that does mess up the model. And actually, at-risk has a wonderful way of addressing that, where you can actually model your inputs as correlated inputs. Here's my last slide. I wanted just to go back to a book. Again, I don't know if you, in your field, you're interested in reliability, but if you do, it's probably a pretty good source, especially if you're a beginner, where it kind of gives you an overview of reliability from practical standpoint. Because a lot of books on reliability actually have a lot of mathematics in them, which is which is fine. But again, if you're a practicing engineer, it's in a lot of cases it's just way too much. You need something more practical, something you can apply, like how to do tests, how to write a test plan, and how to analyze your data without going into fancy mathematics. And I think this book actually kind of serves this purpose quite well. And the fact that it went through 5 editions also kind of helps to kind of make a case that it did pretty well. Okay, with that, I'm not going to go into number of runs. I'm going to turn it back to Jamison in case there are any questions. I know we close to noon right now, but I'm willing to stay over if there are any questions, or maybe answer them later.
Great. Great. Thank you, Andre. Thank you so much. I think we do have a couple questions. I don't see any on my chat panel. I'll check and see if I see any in the Q&A panel. I do. Oh, yes, this presentation is recorded, and so it can be watched at any time. I'll send the recording link out to everybody, probably later this afternoon.
There's also a question about data set available in the textbook. Some do, yeah. The example with washing machine that came from the textbook, and it obviously, I mean, we had just had 1 hour webinar, and there's only so much you can cover. But yeah, a lot of there's more in the textbook, obviously.
Great, and I don't have any trouble sending out a link about your book too. So I know that we're reading it here at Palisade. So, well, oh, I have a couple other questions.
Sure.
Do you also try to minimize the warranty costs by identifying the input parameters so that they can be communicated to design folks?
Oh yeah, absolutely. Yeah, this is actually a great question. Yes, you analyze your warranty, and again, those models, I mean, they can be pretty complicated, but it's actually done 2 ways. And the best way for analyzing warranty and kind of feeding back to design teams, if that was the question, is actually do engineering analysis and see what's actually failing, and do failure analysis, and then communicate it back to design teams. And I think that the best way to handle that is to do in the lessons learned form, where the design team's working for the next product, and if, let's say, it was a problem with a certain component or a certain process. So when it may be late, if it's not ongoing production, it may be too late for that particular product, but with the next generation, if they take this into account, they can actually improve their design process and use those lessons learned. Yeah. So to answer your question, it's better done in the kind of physical level rather than statistical. But if you see, like if you run a sensitivity model and see that something actually stands out, yeah, you definitely communicate that to the design teams and try to reduce that.
Will you be willing to share your model or something similar?
Yes, actually, one of my models was published, and I can send you a paper where we did that. And in fact, it's kind of funny someone asked that. It was a time I spent like a day and a half with people from Ernst & Young, who, and for those who don't know, Ernst & Young, that's one of the biggest accounting firms in the United States. And actually, since warranty forecasting is part of it's part of Sarbanes-Oxley, where the corporations actually have to be very careful how they forecast those numbers. It was audited, and I had to explain them our model and basically show them that what we're doing, that the practice is actually legit, and they had to be okay with that, so we could keep using that model. So then luckily they were okay, but it took a lot of explaining, because those guys are accountants and we are engineers, even though they're pretty sharp. I mean, they're very sharp and knew a lot about statistics and mathematics.
Well, what do you do if you have scant data?
Scant data, meaning like missing?
Yeah, or missing or not enough. Not
complete. It's a tough question, because again, going back to warranty, a lot of data which comes back is actually not a very good data. It has some noise, something missing, or like people who process that particular failure, they forgot to put certain information. There's certain ways of dealing with that. And again, this is probably a topic for another webcast, where you're dealing with missing and incomplete data. In fact, I have one paper I also wrote when we were dealing with missing data, analyzing warranty. I also can send it to you, Jamison, and you can post on with the webinar. Again, I can't offer one quick answer to that, but the bottom line is we are aware of that. And there's certain ways of dealing with missing. There's a term for that, missing and incomplete data. And so we do take that into account.
Good. In the results of the warranty cost simulation, is there a way to know which component is causing the most variation in the warranty cost?
Again, it kind of goes back to the first question. It seems like warranty is generating a lot of questions. Yeah, again, the answer is yes, but again, it's more of a kind of physical engineering analysis type of data rather than statistical data, where you run the model and see models being more sensitive to a certain parameter. Again, it's more like if you have a detailed enough warranty database, then you see something popping up more often, like certain component or certain interface, and again, that shows up as a physical data in your database, and you deal with it in kind of more deterministic, not very statistical way. It's going back to design team and say, guys, we have a problem with this particular thing. I mean, can you fix it for this design, or if it's too late, then make sure you don't use that for future, because it costs us a lot of money, and we don't want that.
Well, Andre, should we let you go?
There's another question. What do you do when you have few data? Can you extrapolate with enough confidence? Well, again, this is not sure I can give you a quick answer. The quick answer is yes. There's all kind of data, and there's ways of dealing with. With like especially in reliability testing, you may have only 2 samples or 3 samples, which is definitely not enough. But sometimes you need to do the best you can. But typically, again, just a quick answer: if you have few data points, then you can do high confidence, but actually your confidence bounds will be pretty wide because your sample is small. Okay.
Oh, this is a good question too. Yes, go ahead, read that.
What do you do? Are we seeing the same thing?
Yes. Sometimes we do. Sometimes we see different.
From Terry.
Yep.
Okay.
Yeah,
would you use this process to set warranty duration?
Yeah.
Oh, yeah, absolutely. Yeah, absolutely. I mean, if you have a model in place, I mean, you can run this model different ways. Basically, you can set a target for, if you say, okay, here's my let me rephrase that. If you have a good model which kind of links warranty cost and have a time and have other parameters, then you definitely can run this model for, let's say you have a target warranty cost and say, okay, where do I achieve this cost? How long it's going to take me? So yeah, I mean, once you have a model, you can run it different ways. Yeah, maybe we should have another webcast just about warranty.
Well, if I'll send out Andre's contact info, and I'm going to follow up later today. And also, if you have any questions, feel free to email me or email Andre, and we'll have more information in the.
Yeah, and I understand exactly where those questions are coming from because I worked in warranty for quite a few years, and I mean, it seemed like people asking those questions facing exactly the same problems we were facing. Yeah, it's pretty common.
And then maybe some other manufacturers may offer, instead of 3-year, they may offer 10-year. And do you ever find yourself saying, well, how would they even do that? Yeah, we're intrigued by that just from a consumer standpoint.
This is a perfect case for Monte Carlo simulation because, again, we're doing forecasting. I mean, we have some idea, but, again, warranty is something we don't know today. We can guess, we can make estimates, but this is something which is going to come back much later. But we need to set aside money now, and that's kind of a lot of forecasting goes into this process, and obviously Monte Carlo simulation.
Well, good. Well, we really appreciate you doing this.
Yeah. Okay. It was my pleasure. Thanks for everybody who attended.
Yes. Thank you, everybody, and thank you, Andre.
Thanks.